Welcome back, fellow tech warriors. This is Lab 404, signing on. For today's mission, we're running a full system scan. This is PC hardware fundamentals, cabling, displays, motherboards, modern and legacy systems. Now get ready, and let's begin. Personal computers and system cases. At its core, a personal computer is divided into two categories: internal component, protected inside of a system case, and external peripherals that users interact with directly. Inside the case, we find the motherboard, CPU, memory, storage devices, adapter cards, and the power supply. Outside the case, peripherals include keyboards, mice, monitors, speakers, cameras, microphones, and external storage. The system case is not cosmetic. It provides cooling, grounding, airflow, and protection. Tower cases typically open to the side. The front panel includes the power buttons, LEDs, and removable media access. The rear panel exposes the motherboard I/O ports, expansion slot, and the power supply exhaust. Those metal plates and shields matter. They prevent dust, reduce electromagnetic interference, and safely route electrostatic discharge into the grounded chassis. Some systems combine everything into one enclosure, called an all-in-one system. They save space, but limit upgrades and repairs. Now we're going to jump into ports, connectors, and data units. A port is the physical interface on the computer. A connector is the end of the cable that plugs into it. Computers operate in binary, using ones and zeros. A bit, lowercase b, is the smallest unit of data. 8 bits make up 1 byte, uppercase b. This distinction matters. Internet speeds are measured in bits, while storage is usually measured in bytes. Mixing them up is one of the most common beginner mistakes in IT, and can lead to some interesting troubleshooting conversations. Now, USB, the universal serial bus. USB is the most common peripheral interface in modern computing. Keyboards, mice, printers, scanners, cameras, microphones, storage devices all rely on USB technology. USB devices are controlled by host controllers. Each controller can technically support up to 127 devices, but bandwidth and power impose practical limits. Now, some of the most typical USB connector types you'll see is the Type A, which is the classic rectangular connector, Type B, which is most commonly used on printers, Mini B, and Micro B, which are mostly legacy now, and USB-C, reversible, compact, extremely versatile, and now the most common standards you'll see in it. Now when you're working with USB, cable length matters. Low-speed devices can handle up to 3 meters. Full and high speed can handle up to 5 meters. Super speed, shorter recommended lengths are necessary. USBs can also provide power. Standard ports supply a few watts, while USB power delivery can supply up to 100 watts of power, enough to power most laptops and monitors. Now, USB evolved rapidly. USB 1 measured in megabits. USB 2 reached up to 480 megabits per second. USB 3 moved into gigabits, and USB 4 reaches up to 40 gigabits per second using USB-C. Now, we're going to dive into display technologies. Most displays today are flat panel LCDs, but not all LCDs are the same. There's IPS panels, which offer superior color accuracy and wide viewing angles. TN panels prioritize speed and fast response time. DA panels emphasize contrast and deeper blacks. Now, there's some more advanced displays, including OLED, where each pixel emits its own light, and Mini LED, which improves LCD backlighting precision. Some key attributes include things like resolution, refresh rate, pixel density, color depth, and color gamut. Higher refresh rates create smoother motion, higher resolution produces sharper images, and wider color gamuts produce more accurate colors. Now these other ones are more legacy, specialty, and edge case displays. Now let's break them down. Now we've got the cathode ray tube displays, or CRT. Let's start with the original heavyweight champion, CRT monitors. CRT displays use an electron gun that fires electrons at a phosphor-coated screen. Magnetic deflection steers the beam to draw images line by line. Some key traits of the CRTs include their bulky, heavy, high power consumption, analog signal input, excellent motion handling, but no native resolution. CRTs commonly use VGA connections and were standard for decades in offices, labs, and classrooms. These are still in use by some old legacy industrial systems, some older medical and lab equipment, and retro computing environments. They are now fully obsolete, but still testable. Alright, now we're going to dive into plasma displays. Plasma displays were once popular for large televisions. Each pixel contained gas-filled cells that emit light when electrically charged. Some of the strengths were excellent contrast, deep blacks, and wide viewing angles. Some of the weaknesses included high heat output, high power consumption, screen burn-in risk, and heavy panels. Plasma displays have been most entirely replaced by LCD and OLED technology, but they remain part of display history and troubleshooting knowledge. Now, touchscreens and digitizers. Touch-enabled displays add a digitizer layer that detects user input. There are multiple touchscreen technologies. Resistive touchscreens are pressure-based, can be used with gloves or stylus, lower clarity and responsiveness, and are usually found in older POS systems and industrial equipment. You also have capacitive touchscreens, which detect electrical conductivity, which requires skin contact, high clarity and responsiveness, and are usually used in smartphones, tablets, and modern laptops. Active digitizers use powered stylus input. They have high precision and are most common in design tablets and professional devices. Now, touchscreens are not just displays, they are input devices as well. We also have e-ink displays. E-ink, or electronic paper displays, are designed for readability, not speed. They work by rearranging charged pigment particles to form text and images. Some of the key characteristics are its extremely low power usage, no backlight is required, excellent visibility in bright lights, and very slow refresh rates. Some common uses are e-readers, electronic signage, and low-powered dashboards. E-ink displays are not suitable for video or animations. Now we're going to dive into projectors. Projectors are still widely used in classrooms, conference rooms, and large venues. There are several projector technologies. LCD projectors use liquid crystal panels, bright accurate colors, and can suffer from a screen door effect. DLP projectors use small microscopic mirrors. They have smooth motion with higher contrast and are often more compact. Laser projectors offer long lifespan, a high brightness, low maintenance, but usually have a higher upfront cost. Projectors commonly connect using things like HDMI, DisplayPort, or VGA for legacy environments. Now we're going to jump into refresh types and backlight variants. Not all displays refresh the same way. First, we have sample and hold displays. Common in LCDs, can usually cause motion blur. You have impulse type displays, which are used in CRTs and some plasmas. They usually offer better motion clarity. Backlighting also varies. CCFLs, or older LCDs, LED edge lit, full array local dimming, and mini LED backlighting. Backlight type directly affects brightness, contrast, and power usage. You also have some specialized and industrial displays. Some displays are purpose-built. Some examples include medical-grade monitors, outdoor high-brightness displays, industrial control panels, and automotive and aviation displays. These typically prioritize reliability, visibility, longevity, and environmental resistance. They may use legacy connectors long after consumer tech moves on. Now you might ask why this all matters. Well, as an IT professional, you won't just support brand new hardware. You'll support old equipment, mixed environments, specialty devices, and systems that just can't be replaced yet. Knowing why a display works, and not just what cable it uses, makes you a stronger technician. Now, let's dive into video interfaces, modern and legacy. HDMI, the most typical, carries video and audio over one cable and dominates consumer electronics. You also have the DisplayPort, which offers higher bandwidth, multiple monitor support, and adaptive sync for gaming. Thunderbolt combines PCI Express, DisplayPort, and power into a single interface. Thunderbolt uses USB-C connectors, but not all USB-C ports support Thunderbolt. Look for the lightning icon if you have any questions. Now, let's talk legacy. VGA is analog only. It uses a 15-pin connector and supports no audio. Image quality depends heavily on the cable quality and distance. DVI comes in multiple variants: DVI-A for analog, DVI-D for digital, and DVI-I for both. Single link and dual link versions affect bandwidth. DVI is largely phased out, but still appear in enterprise environments. Next, we'll dive into storage interfaces, both modern and legacy. SATA connects most internal hard drives and SSDs, supporting up to 600 megabytes per second. M.2 drives connect directly to the motherboard and require no power cable. eSATA was designed for external drives, but lacked power delivery and is mostly obsolete now. IDE, also called PATA or PATA, used wide ribbon cables and master-slave jumper configurations. It has been fully replaced by SATA. You also have optical drives, which support CD, DVD, and Blu-ray. They still use SATA and appear in enterprise and archival systems. Now, let's talk power connectors. Modern drives use SATA power connectors. Older devices use Molex connectors, which can supply 5 volts, 12 volts, and a ground. Some devices have both connectors. Never connect both at the same time, or you can risk destroying the device. Internally, computers run on direct current. The power supply converts household AC into regulated DC voltages for components. Now we have the motherboard. The motherboard is the backbone of the system. It hosts the CPU, RAM, storage interfaces, expansion slots, controllers, system clocks, all kinds of stuff. The CPU socket is manufacturer specific and supports limited processor generations. The CPU requires thermal paste, a heatsink, and active cooling. There's also a thing called passive cooling, which we'll touch on another topic. RAM is a volatile memory stored in DIMMs. Modern systems use DDR4 or DDR5 with channel architecture affecting performance. Now, with RAM, there is no backward compatibility, so it's always important to be aware of what your system can support. Next, we have expansion slots, PCI and PCI Express. Modern systems use PCI Express, or PCIe. PCIe uses point-to-point serial communication with lanes. You have 1 times, 4 times, 8 times, and 16 times. PCIe is backwards compatible, but lane sharing can reduce performance. Legacy systems use PCIe, which relied on parallel communication and typically ran at a lower speed and used voltage-keyed slots. PCI cards cannot fit in the PCIe slots. Now we're going to talk about motherboard form factors. Form factors define motherboard size and layout. You have ATX, which is full size and can support up to 7 expansion slots. You have Micro ATX, which is more compact and up to 4 slots. Mini ITX, which is small form factor, can usually support up to 1 slot. Form factors determines case compatibility and expansion options, so it's always important to understand what you need your system to do. Now onto the motherboard installation process. You always want to review documentation before starting and install the I/O shield. Use correct standoffs, pre-install the CPU and RAM, secure the board without over-tightening, and connect front panel headers carefully. Route cables for good airflow, and skipping these steps here can lead to things like shorts, boot failures, or silent hardware damage, so always be careful when assembling your motherboard. Now, adapter cards. Adapter cards expand system functionality. Video cards generate display output, capture cards record or stream video, sound cards enhance audio processing, and network interface cards support wired, wireless, or fiber networking. High-end cards may require additional power connectors from the PSU. Also have legacy peripherals and cabling. Serial ports, also called RS-232 or COM ports, transmit data 1 bit at a time. They are still used for network device management and industrial systems. The PS2 port connect keyboards and mice. They are not hot swappable and still appear on some enterprise boards. Next, for adapter cables, active versus passive, You have passive adapters which change connector shape only, and active adapters which convert the signal type itself. HDMI to VGA requires active conversion. USB-C to USB-A is usually passive. Using the wrong adapter is a common troubleshooting failure. Another thing to keep in mind is electrical safety and ESD. You always want to disconnect power before opening a system. Electrostatic discharge can damage components at voltages far below what humans can feel, so always handle components by the edges, ground yourself, and respect ESD precautions. And some final best practices to wrap everything up. Match cables to bandwidth and power requirements, verify compatibility before upgrading, document cable placement during the disassembly, and respect legacy hardware. It still exists in the real world. Now, that's mission complete. This is Lab 404, signing off. I'll see you in the next system breakdown.